Hi, BC Scout. These are your day 114 notes. Day 114 is a fairly quick introduction into what are called Maclaurin and Taylor series. So kind of really bringing together a lot of the information that we've looked at within determining whether or not series converge and diverge. And then as we've headed through power series and all of that information, this is kind of what we've been building towards. Well, do you remember day 27? I'm sure you do. It's day 114. Day 27 wasn't that, well, I guess it was a long time ago. But day 127, I actually copied and pasted these three from a summary on day 127, or day 27, I should say. Day 27, we had at that point learned about linear approximation. Okay, so at a specific value of a, using the slope of the tangent line to approximate the function there. And then there's some sort of error associated with that, of course. So here's what the error calculation looks like for a linear approximation. Then we moved on from there and talked about quadratic approximation at some x value equaling a, and the error associated with that. And although I showed you what a cubic looked like, we never actually did a cubic approximation for any of our functions that we were approximating. But here's what that would look like, right? Just kind of building out from there and then going to the next derivative up from our cubic approximation to determine what the max error is there. Well, of course, where we're headed with this is, what if I went beyond cubic and I went to a fourth degree and a fifth degree and so on? We're determining then an infinite series of terms that represents a given polynomial function. So just as a quick visual as to what we have from up above, if I want to approximate the function f of x at some value of x equal to a, we can use a linear approximation. Maybe that would be decent enough for us to approximate values on this function. A quadratic approximation in this example might even be nicer if we go out an additional term and get something that can model the function even a little bit more closely as we zoom in at the point a comma f of a. Okay. But now that we've done with series, we can get even better than that. Okay, we can go to a cubic, a fourth degree, and beyond. And that's what the concept of a Taylor series is. Okay, so extending the process out further on the next page. That's what a Taylor series is all about. So it's a polynomial function p sub n of x such that we have f of a plus f prime of a times x minus a, right? Stopping here would be the quadratic approximation, the cubic approximation. But if I keep going with that infinite series all the way into the nth derivative there at a, that's going to be an approximation for f of x. And wherever we wind up stopping that, if we go to the next derivative and divide by n plus 1 factorial times x minus a to the n plus 1, that's where we're going to see the maximum amount of error occur. And we know there's not a lot of error in our approximations. We're going to see less and less error the more terms we sort of consider in the process here. Okay. So this question here is going to be finding the Taylor polynomial generated by f of x equals e to the x at a equals 0. Okay, so surrounding x equals 0, we know that corresponds with y equals 1 there. The really nice thing about e to the x is think about what we're going to have to do. We have to do f prime of 0 and f double prime of 0 and f triple prime of 0. Well, the derivative of e to the x is always going to be e to the x. So generating those terms within the series is going to be pretty easy for us to do for this given function. Okay, so since all the derivatives of e to the x are in fact e to the x, we would have the following. That f of 0 is 1, and f prime of 0 is 1, and f double prime of 0 is 1. And their notationally here, f to the n, the nth derivative at 0 would have to be 1 as well. So with all of those values at 1, and given the fact that a is 0, it's going to be the following polynomial function that represents e to the x. It's going to be 1 plus x squared over 2 factorial, x cubed over 3 factorial, all the way until we get to the nth term of the series, x to the n over n factorial. So that's pretty impressive that we can model a function based on an infinite series. Okay. So as a quick check, of course, you can type this in the calculator and kind of see what's going on. I only went out 4 terms within the series. But if we go to y equals here and we look at e to the x and y1 and we do y2 as the first 4 terms of that series. All right, let's see. Oops, let me change this real quick. Okay, so let me hit zoom 6, kind of see what's going on there. So we're going to see e to the x come up first, and then eventually we're going to see our polynomial. And it's really tough to tell because once it gets beyond this point, it models that so closely. In fact, if I go back and I change that graphing style again to good old Bubblicious here. All right, so we've got the bubble going. It's going to be a really nice way to trace that path that eventually becomes the graph of e to the x. So look how nicely this fits. And if I could even get a better fit, I'm sure, right? If I had gone out to the next term and the next term after that, because we do see a little bit of separation up there, but pretty impressive that we can determine this infinite series that models e to the x. It's going to be the best approximation surrounding x equals 0, but look at how great it even does beyond that. So pretty impressive things that we can do here. All right. Well, the next question down below says, what is the maximum error within 0.1 of 0 for the third degree approximation? So we have to sort of cut this off at a certain point if we want to determine error. And if we're looking at this for a third degree approximation, then the max error is going to depend on the fourth derivative. So here's what the error looks like for a third degree approximation. So notationally, e sub 3 is what we're looking at here. The error is going to be less than or equal to the max of the absolute value of this expression right here. And we haven't done this in a while, but again, if you go back to, it might be even as early as like day 20, day 21, that's when we really first learned about linear and quadratic approximations. We've done calculations like this in the past. Well, the fourth derivative at c, that's going to be pretty easy for us to find. That's just e to the c. Okay, and a, remember, is 0. So we're looking at this when n equals 3. So here's what's going to happen. We're going to e to the c. This is going to be x minus 0 to the fourth, and then over 4 factorial. And if we're trying to maximize this, we want to pick values that are within 0.1 of 0. That would make the numerator as large as possible. I mean, the denominator is fixed at 4 factorial, so there's not much I can do there. But if I want to maximize this, let's pick really large numbers. I mean, as large as we can make it. Well, the largest I can pick to be within 0.1 of 0 is by plugging in 0.1 for x, and we're also going to choose the value of c to be 0.1. Now, those sometimes change depending on the function that we're looking at, what I plug in for c versus what I plug in for x. But I'll remind you of that as we do more examples. So here's what the error calculation would look like. It would be that the error is less than or equal to e to the 0.1 times 0.1 to the fourth over 4 factorial. That's a really tiny amount of error. Okay, so to be within 0.1 of 0 for a third degree approximation, this is the maximum amount of error that we would expect to come up with. Okay. So we'll definitely do, as we do more examples with Taylor series, some more calculations of error to make sure you're okay with what do I actually sub in there to maximize. Remember, if we're trying to maximize a fraction, the numerator, we want to try and make that as large as possible. If we were subbing in something for the denominator, we'd want to plug something in that would make that as small as possible. Okay. So if we're good with the error on that one, let's do another example where we find the Taylor polynomial generated by f of x equals cosine x, and again at a equals 0. Okay, so same type of process. Let's go out a few derivatives here to see kind of what the polynomial will start to look like when generating these terms. After a certain point, we'll sort of know what the pattern looks like, but let's go out maybe like 4 derivatives and see what happens. Now, the nice thing about cosine, of course, is when I start finding derivatives, we know that it has a very cyclic derivative. So if f of x equals cosine x, the first value for f of 0 that we're going to plug in is 1. First derivative is negative sine. Derivative there at 0 is 0. Second derivative would be negative cos. The second derivative at 0, therefore, would be negative 1. Third derivative is positive sine. Third derivative at 0 is 0. And finally, like I said, if we go to the fourth derivative, we have that brings us back to cosine x. And the fourth derivative at 0 then must be 1. So we're going to see that the patterns among these values at x equals 0 are going to start repeating themselves as well, right? It's going to go 0, then negative 1, then 0, then positive 1. So if you can imagine, there's going to be certain terms that drop out because we're multiplying by 0 as the coefficient. And then the terms that are remaining, those are going to be alternating in signs from 1, -1, 1, and eventually -1 again. So here's what the polynomial starts to look like as you build up these infinite number of terms. I wrote it with the zeros at first, just to kind of get you an idea of, all right, the x term would get multiplied by 0, but the x squared term over 2 factorial would get multiplied by -1. The x cubed term gets multiplied by 0, but x to the 4th over 4 factorial gets multiplied by +1. So the x to the 5th term would drop out, but the x to the 6 over 6 factorial would have a -1 out front. So hopefully you can kind of start seeing what the pattern would look like in general, because that's what we want to come up with, is what is the pattern for the nth term of this series. If you want to try that before I show you my really good answer here, see if you can generate what the series would look like if it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And if you're ready to get the big reveal, here it is. With those terms, here's what we're eventually heading to. We need -1 to the n there for the alternating pattern within the series. But it's x to an even exponent. It's x squared, x to the 4th, x to the 6th, so it's x to the 2n power. Divided by, well, it's an even number factorial as well, which is why we need the quantity 2n factorial. So therefore, what we know is that cosine x is equal to this series right here, which is just so cool. All right. And again, of course, the more you build out terms within the series, the better approximation you'll get. You're going to get a great approximation surrounding 0. Okay, but if you want to extend this out even further, we'll look at the graph in class. But it does say if you want to try it out on the calc, let's go ahead in class, take a look at what the first 6 terms of the series look like compared with cosine x. Okay. All right. That's all the practice we're really getting with Taylor series today. But if you remember the title of the lesson, the title of the lesson was called Maclaurin and Taylor series. And what we don't realize yet until we turn the page is that what we've done in the last 2 examples are Maclaurin series. So here's what we have is kind of a summary on the last page of today's notes. If a function f has derivatives of all orders at x equals 0 or x equals a in general, then here's what the Taylor series polynomial looks like. And that's what we've been generating in terms of our terms. This was defined earlier in the notes. So what's Maclaurin all about? Maclaurin found this pattern just generated by f, specifically at x equals 0. So if you're looking for an infinite polynomial specifically at x equals 0, that technically can be called a Maclaurin series. So the 2 examples that we've done for e to the x and cosine x at a equals 0 or x equals 0, those are actually examples of Maclaurin series. If it's at any other value of x, if it's at x equals 1 or surrounding any other x value, then technically we're looking at a Taylor series. So just in terms of some vocab there, Maclaurin is technically what we've done so far today. So it's really just a special case that we're looking at. Some questions to ask of a series. Does the series converge, and does it converge to a function? We've seen other examples, if you look back at day 111, of series that converge to specific functions. For many functions, the answer is actually yes. Some very common ones that tend to come up on the AP that you must know are the following. And we did these 2 today, e to the x, and we did cosine x. You can imagine what sine x would look like, because the derivatives for sine are cyclic just like they are for cosine. Notice how for sine, we get a bunch of odd degree terms, which might make sense if you know something about what sine is. Okay, and for cosine, you get a bunch of even degrees with this is the nth term. So we definitely have to know these. We'll do more practice that are associated with these 3, because we can actually change these equations up ever so slightly and see a very similar series start to appear. So we're going to get some practice with that as we do more examples with Taylor and Maclaurin. So not the end of our discussion here, just kind of an initial taste of what infinite series can eventually become. But that is it for today's lesson. So more Taylor series in the next couple days. Have a great rest of your day.